I recently finished reading the book String Theory and the Scientific Method by the philosopher Dawid, and that book did cause me quite some headache. The only way I've managed to make sense of it was by drawing a lot of diagrams, so I decided to summarize this in a short slideshow. The book addresses the question whether we have to adapt the scientific method to recent trends in theoretical physics. And before we start, I want to briefly summarize how we refer to the scientific method here. That's the generation of a hypothesis, followed by experimental test, a refinement of the hypothesis, followed by another test, and so on. Let me then introduce you to theory space. Here's my picture of theory space, only the details are missing. Every theory is a curve in this space. If you know something about effective field theories, you will now be tempted to interpret this as the space in which quantum field theories flow. I want you to not do this. I want you to think of the theories in this space as all being structurally different. This space contains everything from Newtonian gravity over Bohmian quantum mechanics to general relativity. So now I add some data to theory space, and some more data, and some more data. And finally, I add a theory, that's the green line, which nicely fits the data, or at least parts of it. Note that we have made an extrapolation of the theory into the unknown that we can then use as a prediction. Now consider we have another theory that fits some other data, and we also extrapolate this theory. It can happen then that the extrapolation overlaps with that of the other theory in such a way that there is no data that can be compatible with both theories. We say that these theories are inconsistent, and since we know that there is no observation that can be in agreement with both theories, we are confident that this cannot be how nature works. Instead, there must be a better theory that does not lead to this contradiction. Knowing that inconsistencies are unacceptable has historically been an important guide to find better theories. Think, for example, of Newtonian gravity and special relativity, or the atomic model and classical electrodynamics. This problem can also arise within one theory itself. Here's an example of a theory that nicely fits all the data, but then comes to a contradiction with itself. We call such a theory not self-consistent. And again, we would conclude that this cannot be how nature works. We would not trust this theory in the troublesome region where it is in disagreement with itself. And we would then go and look for a better theory that does not suffer from this problem. An example is quantum field theory in curved space, and this is why we look for a theory of quantum gravity. So physicists clearly assume that inconsistent theories are not viable descriptions of nature. That's obvious what the physicists say. The philosopher would say, that's non-empirical theory assessment. And that's interesting because it's not part of the scientific method. It's not based on an experimental test. It's based on our trust of mathematics and an extrapolation into a region where we have no measurements. I find that interesting because it wouldn't even have occurred to me to call it non-empirical. If we have learned one thing from the history of physics, it's that mathematics works extremely well to describe nature. So the use of mathematics is clearly based on evidence. That we have made an extrapolation into a region where we have no observation doesn't matter, because even without making a measurement, we know that there is no observation that could fit both theories. That's not the only type of non-empirical theory assessment that physicists make. Let's put in another theory, one that suddenly changes its mind. An example would be the hypothesis that if we turn up the energy of the LHC just a little bit more, we will create a wormhole. And through this wormhole, there will be aliens coming, and the aliens have a warp drive, and the warp drive violates energy conservation, and that explains the cosmological constant. And see, I fitted some other piece of data. Well, nobody would believe that theory, and you would not get it published. So physicists certainly trust their theories to not suddenly break down and do something entirely different. The physicist would say, well, we've learned that it works. The philosopher says, That's interesting because you have implicitly assumed that there are limits to scientific underdetermination, which you couldn't have known by use of the scientific method. So again, you're doing non-empirical theory assessment. Let us go back and look at theory space again. Here we have some data fitted by a theory, and we've made a prediction. Turns out the new data doesn't fit the theory. So then we go and revise the theory. We make a new prediction. And again, we have to go and revise the theory and end up with a theory that fits all the data. Now, the more data we have successfully explained by a theory, the more confident we become that this theory captures some fundamental truth about nature, and the more we trust it. If we look for a new theory, we wouldn't start all over again, but we'd look for something that is structurally very, very close to that green curve. So clearly, the more theory has done for us, the more we trust it. The physicist says, well, nobody will pay me to reinvent the wheel, so I'll instead improve the wheel. The philosopher calls that meta-inductive inference from the success of other wheels. Theories. Again, that's not strictly speaking an application of the scientific method, though. Dawid in his book points out another type of non-empirical theory assessment that is often raised by string theorists, which is that a finding seems more convincing the more surprising it is. For the physicist, that's summed up in the saying that the most interesting discoveries begin with somebody mumbling, "That's funny." For the philosopher, that's the argument of unexpected explanatory coherence. So Dawid in his book starts out with quite general observations about how physicists assess the promise of theories, and then focuses on string theory in particular. To look at the final argument that is often made by string theorists, let us go back to theory space. Suppose we have a theory that successfully fits all the data, but it extends through regions where we have not tested it and cannot test it anytime soon. Is this theory unique, or can there be another theory that does the same thing? String theorists claim that given all the data that we presently have, there is only one theory that can explain it all, and that conviction is mostly based on the observation that there exists presently only one very dominant research program for such a theory, and that is string theory. So they think that we do already have sufficient data to deduce one final theory, which may be correct. The physicist says, well, you're far from proving anything like that, and making such a proof, what do I care? The philosopher says, that's interesting, because if true, it means string theory tells us that there are limits to global scientific underdetermination. Since it may be possible that there is indeed only one theory that can consistently explain all our present observations, some people think that if we find one theory, that must be the one. The physicist remains skeptic. The philosopher calls that the no alternatives argument. And I wonder why Dawid in his book never mentions asymptotically safe gravity, which arguably does not attract as much attention as string theory, but it is also claimed to consistently combine general relativity with the standard model. Okay, now let me summarize what we have so far. Dawid in his book collects the arguments raised by string theorists in favor of the theory, and he identifies the following three types of non-empirical theory assessment. The meta-inductive argument, saying that if something has worked previously, it's reasonable to trust it and use it again. The no alternatives argument, saying that we haven't yet found anything better, so maybe there just isn't anything better. And the argument of unexpected explanatory coherence, saying I trust this finding because my colleagues found it by accident. Now, Dawid's main point is that if string theory is scientific, then these arguments should be part of the scientific method. That's my summary of Dawid's book, and now I have some comments on this. First, I want to say, though, that I think he has identified these arguments very well. I don't think it's a complete list of non-empirical assessments that are being used in the community right now, but these are important points. One can question whether these are good points, but that's a question I will address some other time. Right now, I want to address the question whether we should change the scientific method to integrate these non-empirical assessments. For this, let us look again at the scientific method. The scientific method as the philosopher thinks of it, the circle of hypothesis and test. That's a nice idea, but of course it's not how science works in reality. To begin with, this method has a chicken and egg problem because it doesn't tell us where a good hypothesis or an experiment comes from. Where do they come from? Well, they come from ideas that are either hypotheses coming from theorists, then being put to test, or ideas for experiments coming from experimentalists, and these feed the circle. And maybe that indeed was how science worked 400 years ago, but it is clearly not how it works today. The scientific communities have grown a lot, and there are many theorists and experimentalists who constantly come up with ideas that they want to be taken seriously. Nobody can read all these papers, and we can do all these experiments. So since Dawid's book is about theory assessment, let us focus on the theoretical side of this. What happens in practice is that all these many ideas are heavily filtered by the community, and there are only very few ideas that survive and ever get taken seriously enough to be considered promising and interesting enough to be tested. And just to prove that I can also make up words, let me call this hypothesis preselection. There are many aspects that go into hypothesis preselection. There are, for example, guidelines for good scientific conduct, the expectation that your research result or your computations are reproducible. There is peer review, and there are many other requirements for good scientific procedure that depends on the research area. And then there are the community standards, which are typically never written down anywhere, but which decide whether an idea will be accepted by the community or not. In theoretical physics, for example, it's mandatory that your theory is based on mathematics, and it has to be consistent, at least in the region where you claim it is applicable. The non-empirical theory assessment that Dawid is talking about is exactly this. It's community standards for hypothesis preselection. Look in particular at the non-alternatives argument and the unexpected explanatory coherence. This is basically the observation that many people are peeing at the same tree and that they trust their colleagues better if they didn't get the result they expected. But these are social arguments, not philosophical arguments. That leaves the meta-inductive inference, which relies on the limits to scientific underdetermination. It seems to me that there is something to this argument that is probably true under certain circumstances, and these circumstances seem to be fulfilled in our universe. But how to make this more formal? I don't know. As a final point, I want to come back to the question of whether consistency requirements are scientific. I previously said I think they are, because we know that there is no data that could fit an inconsistent theory. But that is true only if the inconsistency is at least in principle observable, and so it has a philosophical aspect to it. Freeman Dyson has famously argued that quantum field theory and general relativity aren't really inconsistent because we might not ever be able to observe the region in which that inconsistency might happen. If you don't like Dyson's argument, then maybe you should keep in mind that black hole complementarity rests on the idea that an inconsistency with quantum mechanics is totally okay as long as nobody can observe it. So in summary, I think it is a great book, and Dawid has very well identified some important trends in theoretical physics. However, I also think that this analysis is incomplete without also taking into account the sociological developments in the community, and I do not think that we have to revise the scientific method.